In here, sticking with the theme of oxidation number, here are a couple of things that we need to be aware of when it comes to how this is going to be important in electrochemistry. First is the following. Here we need to highlight or recognize that this here is assigned to each element in the chemical reaction, and we're going to look at examples of this in future videos. Now the second point here focuses on the idea that this here is shown what at the top right of a or an element symbol in a particular chemical compound. Like for example, where we have this particular element which is hydrogen at the top right, usually is shown when it loses an electron, and we have the oxidation number to represent as 1 plus. Now the third one here focuses on the idea that this shows how many electrons is gained or lost in or by an element that is in a particular reaction. For the first step here, or what you need to understand, when an element loses an electron, this here is known as what? The oxidation process, and this is accompanied by the other species that gains the electron, and this here is a process known as the reduction. And what does that mean? According to our previous video, for oxidation we have what is known to be an increase in the oxidation number. However, for the reduction process we have a decrease in the oxidation number. Now the next step in this video here is we're going to look at the following rules, and how these rules here will enable us to easily determine various species and also determine other species in a particular compound when those compounds are react with other compounds in a specific reaction. Now for the first step here, when it comes to the rule says that when you have a charge to be equal to 0, what does that mean? That means that you have the elements to be what? To be neutral. And we have a couple of examples like Fe2, we have Cl2, we have H2, we have O2, and when you look at this, there are other elements as well that are shown to be what? Diatomic, which means they have identical atoms that are bonded together, usually in pairs, and these here are known as the half B brain cool. And this here enable us to access those elements on the periodic table that are diatomic and neutral, but at the same time we have other elements on the periodic table that are not diatomic but they are just an atom. Like for example, we have sodium, we got copper, we got iron, and all these guys here, when they are not reacting at all in their natural form, their oxidation number as shown at the top right corner is equal to 0. And this here is the first rule to remember when it comes to oxidation number. Now the second rule here looks at for single atomic ions. This here implies that we now have elements that undergo a reaction, and this here has an interesting characteristics, and these interesting characteristics will be revealed on the periodic table later. And this here is usually shown when you have an element like F negative, or we have Na positive, or we have Cu2 positive, or we have another example which is Fe let's say 3 positive. And this here, when you're asked what is the charge, which shows that this here is a connection with it directly to the oxidation number, because the oxidation number of fluoride here is -1. That means the charge here is equal to what? -1. Now for the next one here, because the oxidation number of sodium is 1 plus, this here means that the charge of sodium ion is positive 1. For in this case copper 2 plus, the charge of this here is equal to what? Positive 2. And finally for iron, because in here iron 3 plus, this tells us that the charge is what? Plus 3 or positive 3. And so this is how we are able to make that connection between the oxidation number and the charge of that particular species. And what does this mean? The charge tells us that this particular fluoride here has done something, which is it's gained 1 electron. For sodium 1 plus, it has a charge of plus 1 because it lost what? 1 electron, which makes it to be a net charge of positive because it has more protons than what? Electrons by 1. And for copper 2 plus, it loses 2 electrons. That means the number of protons is plus 2 more than that of the number of electrons. And for iron, we have 3 plus, in this case positive 3, which means that the number of protons is 3 more than the number of electrons. So that is how you think about this when it comes to this particular setting of the oxidation number related to the charge. And the final one here is we're going to dive really deep into what? The groups on the periodic table, and how this here is going to help us to determine various specific charges that are common in some groups on the periodic table. And this here is as follows. In here we have a general view of the periodic table. I know we left out the 28 elements in that particular block, usually around here, but here we're going to look at the interesting characteristics and relationships between elements in a group, and how that might help us understand the relationship between the oxidation number and that of the charge. And so first off is this block right here, and this block is going to be labeled to be the group 1, which are the alkaline metals, and this here has a charge to be what? Plus 1, and its oxidation number, which reflects the charge, is what? 1 plus. For example here, this element right here is lithium, and lithium, when you look at the particular rectangle, you see 1 plus in there. This means that lithium, alongside other elements that are on that group, they are able to what? Willingly lose 1 electron, and this is needed for them to be stable and obtain their octet. Now take note also that this is positive 1 because the number of protons is 1 more than that of the electrons after the loss of that 1 electron from its neutral state. Now moving on to another group here on the periodic table is the other side here, which is assigned to be group what? 17, or you can just say group 7a. And what are they? This here represents the halogens, and the halogens, they exhibit something quite interesting, which is they are really electronegative, and they are always willing to gain an electron. Therefore the oxidation number is always 1 minus, and this results in that charge to be what? -1. Like for example here we have fluorine, which is the most electronegative element on the periodic table, will always gain an electron from any other elements right here on the periodic table, except for this side right here. But just keep that in mind in terms of fluorine. This here, when you look at the rectangle on the periodic table, you see a charge here which is 1 minus. So this here is the oxidation number, which means that it always has, when it reacts, it always has 1 electron more than the number of protons. So that is something to keep in mind. Now there is something quite interesting when we look at group 1, and this here comes down to this particular element right here, which is called hydrogen. And hydrogen usually when they react with something else that is more electronegative than it has addition number of 1 plus, and this here shows that hydrogen is always willing to what, lose that 1 electron. However, there are exceptions to this rule here where hydrogen is not that case, but in this case hydrogen is going to be -1 or 1 minus, and for the oxidation number to be 1 minus, it must gain electrons from something that is less electronegative. Like for example, we have calcium hydride, and this here is a great example where if you look at the oxidation number of calcium, you'll notice that calcium has oxidation number of 2 plus, and when you look at the hydrogen, individual hydrogens, the first one we have 1 minus, and the oxidation number of the other one is 1 minus as well. And because the total number of charge here is equal to what, 0, this here means that this here has to be equal to 0 in terms of the charge, and this here is proven by doing your little math. 2 plus what, -1 plus what, -1, and this here is equal to, yes indeed, 0. So this here is one case scenario where hydrogen has a negative charge, and that is the exception to the rule. And the other one can be a proof that hydrogen is positive one is when you have water present, and when you have H2O, for example, we have oxygen is always 2 minus in terms of its oxidation number, and we have a hydrogen to be always, in this case when you do the math for the oxidation number of this compound to be equal to 0, that means the charge must be equal to 0. So that means we must have +1 for both hydrogens for this here to be what, true, as our answer. So that is something to keep in mind in terms of the comparisons. Now, speaking of oxygen, on the periodic table we have this particular region here where oxygen lies, and this here implies the following, where oxygen is always a charge to be equal to -2, and so that means its oxidation number must always be 2 minus. That means it always gains 2 electrons, and since this here is true for oxygen, there are some exceptions to this rule where oxygen is not 2 minus in terms of the oxidation number, and this exception here is where oxygen is what, 2 plus. And you might be wondering, how is this possible in terms of the oxidation number to be 2 plus, and that results in our charge to be +2. And this here comes into play where you have some cases where this particular oxygen 2 plus is reacting with fluoride. So in here, for example, we have OF2, and this here has a general charge to be oxidation number to be equal to 0. So that means our charge here must be equal to 0 for this sum of oxygen oxidation number or charge and that of fluorine, which in this case we have 2 fluorides here, and fluoride we know that its charge is -1 for 1. Therefore this here shows that oxygen is equal to what, +2 in terms of its oxidation number. And the other case scenario is for water. We have oxygen here to have its oxidation number to be what, 2 minus. So these are the interesting things where oxygen has exceptions, and there are many more things here for oxygen with regards to its exceptions. We have this case scenario where oxygen has its oxidation number to be 1 minus, and this here can be found in hydrogen peroxide, and I will encourage you to try figuring this out in terms of what the oxidation number of oxygen here, one oxygen atom is, and you should be able to figure out that yes indeed oxygen here has its oxidation number to be 1 minus, and in this case its charge is equal to -1. And also we have barium O2, and this here also interestingly do have its oxidation number here to be equal to, for one oxygen, -1. So pretty impressive stuff right here with regards to oxygen. Now, in terms of what we talked about here with regards to the general charge of a particular compound, this here leads us to the next rule, where the sum of the charge in a neutral compound is always equal to 0. And for polyatomics, we have the charge to be equal to the top right corner. Like for example, the first scenario, we have H2O, and this here we don't have, or we don't see any charge at the top right, so this here is assumed that its oxidation number is equal to 0. Therefore its charge must be equal to 0 for the sum of the oxidation number, which translates to the charge, to be equal to 0, as shown right here, which we discussed on our previous side of this video, where we have two hydrogens which are each +1 in terms of their charge, plus we have one oxygen whose charge is -2, and this here is equal to 0. Now we have another one here, which is the other case scenario. We have an example which is sulfate, and sulfate has oxidation number to be 2-. Therefore this here, when you do the sum of sulfur's oxidation number plus we have that of our oxygen's oxidation number, but we have 4 of them, and in here oxygen has 2- to be its oxidation number, this here should be equal to what in terms of the charge? -2. And so if you do the math with regards to what is the oxidation number of sulfur based on the charge, we can do this here by having a -8 on this side, and this here is equal to what? -2, and we still have a sulfur, and remember here that it is going moved to the other side to become +8. Therefore sulfur here will have a charge to be equal to what? +6. So that means sulfur in some ways has to use its 6 electrons and interact with the oxygens that are present in the system. So it's pretty impressive stuff right here with regards to how the overall charge of a particular compound relates to the overall oxidation number of that particular compound, as shown and used right here. So that is it for this, and the final part here is the following. In general, on the periodic table, all the metals have their charge to be a positive charge, and this here is in contrast to the other side, which are more electronegative atoms or elements, and these here have a negative charge, and whatever value that means, it depends on, for the negative charge, how much they are willing to gain electrons. However, for the positive charge, how much they are willing to lose electrons, and that is something to keep in mind. So I hope you found all these rules informative, and I hope this here will help you to be successful in different questions that we're going to talk about on our next video. Please go down into the comment section and let me know your thoughts about the oxidation number rules, and see you all on the next one. All the same, stay smart as always and believe in yourselves.